This is Lab Report 5, Falling Slinky by Jack Palacio. So an introduction to this lab. The purpose of the experiment is to observe the motion of a slinky when dropped from a height h. The system is the slinky, the hand that holds the slinky, and the earth and the surroundings is everything else. And a brief overview of the result is the bottom part of the slinky remains still until the top part of the slinky comes in contact with the bottom. So for the physics principles applied in this experiment, Newton's second law states the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass, which also is just saying F equals ma. The gravity force is the fundamental force that pulls objects with mass toward one another. In this case, it's the slinky and the earth. This is just saying that Fg equals work equals mg. And also the slinky force is the tension created by the coils pulling on each other. The tension force would just be mg, and the gravity force is negative because the earth is pulling the slinky towards the center of the earth. So here was the experiment. This was the top part of the slinky in his hand. This is the bottom part. As you can see in the Y position, it stayed the same up until here, and that was when the top part reached the bottom part, and then it started to fall towards the earth. The initial height was 1.97 meters, and an estimate for the mass of the slinky was 0.225 kilograms. So the initial conditions for the code, I've just put in everything from the tracker. This was the estimate of the mass. This was the position of the slinky. It was motionless, so it had the zero velocity, and then the times. This was gravity constant, and this is the drag constant. This was just found with guess and check. So this is the first while loop. This is before the top part hits the bottom part of the slinky. The work is just negative mg, and then the force of the slinky is just negative work. And that makes sense because these two should cancel out because the bottom of the slinky is not moving. Here's the velocity update formula and the position update formula. And then, yeah. So then we'll move on to the second while loop. This was after the top part has reached the bottom part of the slinky. Same thing for force of gravity, but now we have the drag force, and then the net force is just the drag force plus gravity force. And then this is all the same as the first while loop. So here was the results that we got. This was the pink was the observed motion, and this was the predicted motion. So it did predict that it should take in a little bit longer to reach the bottom of the slinky. Obviously, that doesn't account for other forces that are acting on it, such as air resistance, which goes into here. Human error for tracker not clicking in the center of slinky every time, and then other errors, external forces not being accounted for. So for what if the same slinky was dropped on the moon from the same height and same length, the time that it takes for the top of the slinky to reach the bottom of the slinky would remain the same. Even though the g constant is different, because the slinky stays the same and the stretch length stays the same, it does not affect the time. So for what does it mean? The delay shows that the physics of the collapse is governed not just by F equals ma, but by wave mechanics as well, where the movement of the top must wait for the wave of tension release to reach the bottom.